Video number 2, Input Parameters for SIESTA Simulation. The parameters you need to specify to set up a SIESTA simulation include atomic coordinates for the structure you want to study, exchange correlation functional, basis sets, k-point density, and the mesh cutoff. For the atomic coordinates, you can get them from literatures or experiment, or you can generate your own atomic coordinates using 3D molecular visualization software such as a Crystal Maker, VMD, or SIESTA. Exchange correlation functional describes interaction between electrons. Basis set described the wave functions. K-point density refers to K-point sampling in Brillouin zoom. Mesh cutoff specifies the spacing of a 3D grid to map electron density. Let's look at an example for aluminum FCC structure simulation using SIESTA. So the first thing you need to specify is the lattice vectors. This is A, B, and C. And then you need to provide atomic coordinates for each atoms in the unit cells. So for this aluminum FCC crystal structures, and there are 4 aluminum atoms per unit cell, so that's why you need to provide their atomic coordinates in X, Y, Z, and you can see the atomic coordinates are fractional. Exchange correlation functional. This is the Schrödinger equation with the expanded Hamiltonians. And this term represents exchange correlation functionals for the interaction between electrons in a materials. And this term also considers same and opposite spin effects. There are 2 approximations to determine this exchange correlation of functional, including LDA, local density approximation, and the GGA, generalized gradient approximations. Normally, if we need to simulate the crystal structures, we would choose the LDA to determine the exchange correlation of functional. And for surface and the molecules, we would choose the GGA to determine the exchange correlation of functional. The code SIESTA uses a linear combination of basic function, which is also called a basis set, to determine wave function. What you need to remember is a larger or more complicated basis set leads to a more accurate simulation, but it takes a longer computational time. So in SIESTA, single zeta, representing SZ, is a minimum basis set for some quick simulation test, but not accurate enough. Double zeta, DZ, is more accurate because it considers the radial flexibility of an atomic orbitals. DZP, the P stands for polarization, and which considers electron spin effect in the wave function. And it considers the angular flexibility of an atomic orbitals. Normally, we choose DZP as a basis set, and which is already accurate enough for any type of simulations. K-point density. Any crystal structure can be represented in 2 spaces, including real space, XYZ, and the reciprocal space, Brillouin zoom, in KX, KY, and KZ. Any point in the Brillouin zoom can represent a K-point. So there are an infinite number of discrete K-points, well qualified to be a wave functions. And the wave functions and also the band structure vary smoothly over the Brillouin zoom. So we don't need to include an infinite number of discrete K points. We just need to sample a finite number of the K points that represent each small region. Each K point contains rich information, including wavelength and the kinetic energies. And all the energies on each K point form band structures. In that way, more K points lead to a more accurate simulation, but it costs more computational time. Mesh cutoff. In SIESTA, mesh cutoff means an energies corresponding to a finite 3D grid for the calculation of electron density and potentials, because the electron density and potentials are the function of position. So we need to define the spacing of the 3D grid to map the electron density and the potentials. What you need to remember is that the larger mesh cutoff leads to smaller spacing and the more dense 3D mesh, resulting in more accurate simulation, but longer computational time. Here I want to repeat the parameters you need to specify to set up a SIESTA simulation. Include atomic coordinate for the structure you want to study, exchange correlation functional, basis set, K-point density, and mesh cutoff. For atomic coordinate, you can generate using Crystal Maker, Vestas, or VMD. You can also try to find the atomic coordinates from literatures or experiment. Exchange correlation functional basis set, K-point density, and mesh cutoff, and you need to optimize them before you run any SIESTA simulations. So in the next slide, and I will explain how to optimize those 4 parameters. Whatever materials or properties you want to study using SIESTA, you need to do the following 3 steps. Step 1. Optimize K-point density, mesh cutoff, basis set, and the exchange correlation functional by finding the lowest total energy of the material you are interested in. Step 2. Using the optimized parameters, run geometry optimization to find the ground state structure of the materials. Step 3. Using the optimized parameter and the ground state structure of the materials, you can run further calculation to study other properties of the materials. For example, you want to determine if the material is a semiconductor, metal, or insulator. You need to run electronic band structure calculations to find the band gap size. Here I list what a SIESTA simulation can do. First is to find ground state structure of materials. SIESTA can also determine electronic band structures. From the electronic band structure, you can study band alignment and the band gap size. SIESTA can predict different properties, including electronic, mechanical, optical, thermal, magnetics properties, etc. For this class, we will focus on mechanical properties. Learning resources for computational modeling class include lecture videos, PowerPoint slides, research papers, must remember note, and for DFT concepts, and I will post it on the Blackboard later. And also the Richard Lasser's book, Introduction to Computational Material Science, Fundamentals to Applications. We only focus on the Chapter 4, Electronic Structure Methods. And you will also do the in-class and take-home questions. Before you step into the first computational modeling class, I want you to do the following things. First is to watch lecture videos, video number 1, video number 2, and then register on NanoHub through this link. And get your account and log in. After you log in and go to My Tools, select MIT Atomic Scale Modeling Toolkit as your favorite tools, and try to launch the MIT Atomic Scale Modeling Toolkit and see if it works. Finally, download and install the VMD through this link.